And today we will be doing FRQ 2018 number 1, which deals with stoichiometry, solutions, thermochemistry, and ionic bonding. The question begins by saying, a student performs an experiment to determine the value of the enthalpy change, or delta H, for the oxidation-reduction reaction represented by the balanced equation above. Part A. Determine the oxidation number of chlorine in sodium hypochlorite. To do this, we know that sodium is always +1. And the hypochlorite ion is -1 in general, and oxygen is always -2 except in special occasions, so that makes chlorine +1. Part B. Calculate the number of grams of sodium thiosulfate needed to prepare 100 milliliters of 0.5 molar sodium thiosulfate. All we need to do is multiply the concentration by the volume in liters. Make sure you convert to liters. And then multiply it by the molar mass, which is 158.1 grams per mole. And our result is 7.905 grams of sodium thiosulfate. In the experiment, the student uses the solutions shown in the table below. Part C. Using the balanced equation for the oxidation-reduction reaction and the information in the table above, determine which reactant is the limiting reactant. Justify your answer. What we need to do here is multiply the concentration by the volume in liters again for each one of the reactants, and then convert into one of the products. Because each reactant has the same concentration and volume, I didn't feel the need to show a recalculation of the amount of each one of the reactants. I also chose to convert each one of the reactants to water because it had the simplest molar ratio, as water only has a coefficient of 1 in the equation. All you need to do to find the limiting reactant is convert each one of the reactants into a product and then compare the results, and whichever one is the lowest is the limiting reactant. We can see here that sodium hypochlorite produces the least amount of water, so that's the limiting reactant. The solutions, all originally at 20 degrees Celsius, are combined in an insulated calorimeter. The temperature of the reaction mixture is monitored, as shown in the graph below. Part D. According to the graph, which I will show on screen, what is the temperature change of the reaction mixture? Temperature change is always equal to T final minus T initial, so we just need to look up what is T final and T initial. And T final is estimated to be at 32.5 degrees Celsius, and T initial is given to us at 20 degrees Celsius. So the temperature change is 12.5 degrees Celsius. Part E. The mass of the reaction mixture inside the calorimeter is 15.21 grams. 1. Calculate the magnitude of the heat energy in joules that is released during the reaction. Assume that the specific heat of the reaction mixture is 3.94 joules per grams degrees C, and the heat absorbed by the calorimeter is negligible. To do this, we need to use the formula Q equals mass times specific heat times temperature change, and everything has been given to us or we calculated it beforehand. So all we need to do is multiply mass times specific heat times temperature change. And our result is that Q equals 749 joules. Part 2. Using the balanced equation for the oxidation-reduction reaction and your answer to Part C, calculate the value of the enthalpy change of this reaction, delta H, in kilojoules per mole. Include appropriate algebraic sign with your answer. To do this, we need to use the same formula as before, but replacing Q with delta H. We can use the same values as before except for mass, which in order to calculate that, we need to use the mole amounts from before from each of the reactants and convert into the other reactants. Remember, the sodium hypochlorite was the limiting. So I pre-calculated all of those by multiplying by the molar ratio. And now we need to multiply each by their own molar mass, which I've also pre-calculated. Our final step in calculating mass is adding up all of the individual masses of each of the reactants, and our result is 0.0837 grams. Now, we plug that into the equation for delta H and multiply by the specific heat and the temperature change. Our answer is 4.123 joules per mole, and then divide by 1000 to convert to kilojoules. So our final answer is 0.00412, and that's positive because it is absorbing energy. The student repeats the experiment, but this time doubling the volume of each of the reactants, as shown in the table below. Part F. The magnitude of the enthalpy change, delta H, in kilojoules per mole, calculated from the results of the second experiment, is the same as the result calculated in Part E2. Explain this result. The reason that enthalpies are the same is because enthalpy does not depend on volume. Part G. Write the balanced net ionic equation for the given reaction. What I do for these is I split each compound into its ionic parts and then cancel out ions that are on both sides of the equation. There are 8 sodium ions on each side of the equation, so those can cancel out. Also, there is 1 hydroxide ion on both sides of the equation, so those can also cancel out. Now that there are no more ions to cross out, we rewrite the equation and make sure it is balanced. There are 2 sulfurs on the left. 3 plus 4 plus 1 oxygen is 8 oxygens, 4 chlorines, and 1 hydrogen. And on the right, there are also 2 sulfurs, 8 oxygens, 4 chlorines, and 1 hydrogen, so it is balanced.